Line P5 learning task for high voltage instrument transformer calculations is what we're going to go and take a look at. Instrument transformers were covered off in line P3, which was our first three-phase transformer module that we went through. And we talked about a couple of things that they have as standards. One of the things that they're going to have as a standard for my PTs or VTs, depending on which one you want to go and have, is that my secondary is always going to go and put out a rated value of 120 volts. Whatever we have in our primary, it could be 14.4 kV that we might have, or whatever it's going to be, is going to be rated against a secondary value of 120. We'll just leave this as an open box. We'll just insert whatever our high value is into that one, and it'll be to a ratio of 120. Our CTs are going to also go and have a standardized secondary, and the standardized secondary is going to go and be 5 amps. And once again, whatever we've got for a primary side that we're going to be feeding in is going to go and get placed inside there. It might be 300 amps to 5, it might be 800, whatever it is, based upon the size of the system itself. There are going to be standard sizes inside here. You're not going to have, oddball sizes. And what we get here on the secondaries is always going to be based upon full rated flowing in the primary. In other words, if we would have a 400 to 5, we would only get 5 amps when we get 400. If we would go and have only 200 amps, we would get half of that, 2.5. But if we would get 600 amps, we would get 7.5 amps that would be flowing out of this. Same with my PTs. If I've got a PT that is going to be rated, we'll just put this thing to 1,000 volts right now because it's an easy value to work with. If it was 1,000 to 120, if we were at 1,000 volts, we would have 120 out. If we were at 500 volts, we would get 60 out, or if we were at 1,500, we would go and have 180 volts out. So it's always going to be scaled off of the same voltage ratios as what we have before, turns ratios, etc. But when we look at these things, we're going to read them always as being to 120 or as being to 5. Okay, we're going to work off of a lot of the same calculations of what we saw inside of previous learning tasks over here. What they're looking for is they're just looking to go and see what we have off of each of our secondaries. Once again, I don't want us to go and start tripping balls on what the secondary is over here. The secondary is connected inside of a Y like that. That's fine, but it doesn't actually do anything for us. It makes the whole installation safer, but it doesn't affect any of our windings, because if I take a look at any of my winding voltages that I'm reading, I can see that I am only reading this voltage with that one over there, and I can see that I'm only reading this voltage with this one over here, even though they're connected to the Y, and that I'm only reading this voltage with this one over here. They're going to go and give me ratios of my C to neutral voltage that I'm going to have with my A to neutral, because what I'm seeing is that I'm measuring across from my A line over to my neutral line with each of these. It says calculate the following values if each PT has a voltage ratio of 69 kV to 120 volt and if each voltmeter reads 113 volts. So if I have got a 69 kV to 120, that's going to be my ratio over there. Now I can simplify this down into a smaller, more simple ratio if I want, or I can work with the 69 over 120. We're going to work with the 69 over 120. If I take a look at what my voltmeters are actually reading, they're not reading 120, they're reading 113. Which means that by default, I don't even have to do a calculation before I know that we're going to have a value that's less than 69 kV on my primary. Well, how much less? We can't just go guessing when it comes to instrumentation. Let's go and calculate this out. We're just going to go and take our secondary actual side, 113, and we're going to multiply it by my ratio, 69,000 over top of 120. And that's going to go and bump us up to our high side. Let's go and do so. We are going to go and take 113 multiplied by 69,000 divided by $1.20, which is going to go and get us to a value of 64,975 that we will have. Okay, let's go and chuck in that number over there. So on my high side, 64,000 975 volts. That's what each of these is reading. If I take a look at it, I see on my high side that I am connected in Y, and so this is going to make a difference for us, because now that we know that each of my windings here is 64,975, therefore I know that I should have a line value that's going to be root 3 greater than that. Let's go back to our calculator. We still have the 64,975. We're just going to multiply that by root 3, which is going to get me out to a value of 112.54 kVA. My line value of voltage, 112.54 kV, kilovoltage. Beautiful. Simple, straightforward. Just remember, we're able to go and use this as a ratio like this. I could have also simplified it from 69,000 over 120. If you want, it's allowable. We'll just show that 69,000 divided by 120 means that the actual turns ratio is going to be 575 to 1. So I could have done this times 575 to 1, which we simplify out to just become 575 at that point. We could have used that inside there because that's what it's equivalent to. Okay, let's go take a look at our next one over here. Example number 2. Calculate the PT turns necessary for the voltmeters to read 120 volts if the system has a line voltage of 14.4 kV. Well, if we take a look at what I have connected on the primary side, I see that my primary is going across from line to line over here. So since I'm going across from line to line over there, I'm going to be looking at, well, if this is going to be a line voltage of 14.4, I'm going to see that I'm going to stick the whole 14.4 kV over top of that winding. And over here, this is going to be 120 volts, so really, if I was buying a instrument transformer, I would get one that is going to be rated at 14.4 kV to 120. But since in this case they're asking for the turns ratio, it's relatively easy for us just to go 14.4 over top of $1.20. Gets me to a value of 120. So we would need to go and have 120 to 1 rated transformers that are also rated for 14.4. This is why we like to go and see these ratings, that they're actually going to be 14.4 to 120, because if I just look at 120 to 1, that doesn't tell me anything about what good my insulation is on there. You know, is this insulation only good for 600 volts, and we're just doing a 120 to 1 ratio, or is the insulation going to be good for 10,000 volts? Is it going to be good for 500,000 volts? That's why we like to see these ratios out like that, because first of all, it tells us that it's a PT, and secondly, it tells us the size of the system we can safely go and utilize this on. Okay, next one that we're going to go and take a look at is going to go and be my CTs. Once again, my CTs over here are going to go and give me a reading off of just what they have going and pulled through them. I see that the CT connection is once again on the low voltage side connected Y. Once again, let's not worry about that, because if I take a look at the actual CT, the CT itself is just reading that loop, that ammeter. The CT itself is reading that loop with the ammeter, and the CT itself is reading that ammeter with the loop. There is no complete path for voltage to go from, this guy to that guy and all the way back and forth. So we never have anything where, something from here is going to be going, up through here and then, traveling over and stuff, because ultimately we see that we don't have more than one point connected on each, so there would never be any return path. So just know that we connect them in Y. This is for safety, and so that we have got everything tied to a central neutral point, etc. But we're still reading just the individual current we're going to go and have. It says each CT has a current ratio of 12,000 to 5, and the ammeter for line A is reading 38 amps. Well, if we know what we have got for our ratio, 12,000 to 5, 12,000 over top of 5 amps, we could just go and take that ratio and multiply it by what our actual reading is over here, 3.8 amps. So let's go and do that. 12,000 divided by 5. Oh, let me just clear this. Let's bracket this out first. 12,000 divided by 5 multiplied by 3.8 gets me to a value of 9,120 amps. That's what I've got going through this 9,120 amps that is going out to my load. Remember, it is my load that is in charge of pulling this current. And this current, as it flows through the CT, is what's generating this one over here. This device, this CT, and this ammeter here is not seen as a load to the system. It is just governed by the system itself. Ultimately, it is the amount of current that is flowing out to the load over here that determines the line current that is then going to go and determine this. That means that even if I were to go and short across here, we would never have more than, in this case, 3.8 amps that would be flowing through that shorted bar and through these shorted out windings over here, because once again, as we said before, it is the load over here that is pulling this 9120 amps through here, which is then giving us this 3.8. This is why it's safe for us to go and short out a CT. And do we short out a CT? Absolutely. We always short out our CTs anytime that we are going to go and pull the actual metering element out of here. Okay, next one over here. We're going to go and use CTs to go and measure phase currents. And if we measure our phase currents, then we can go and figure out our line currents as well. Once again, do I care about the fact that I have got this line connected across here inside of a delta? Absolutely. Or inside of a Y? Absolutely not. Because we're going to see that the current generated by this CT is only going to go to this meter. And same with the other subsequent meters there as well. The reason for that Y point, safety, as we have already said so many times before. All right, let's go and calculate the following values. If the ammeters read 3 amps, when my delta connected loads each draw 4.8 kiloamps, that's 4.8 thousand amps of current. So what's the current ratio of each CT, and what is the line current of my primary ratio? Well, we don't know what the ratio is yet, so what we're going to do is we're going to go and take this 3 amps that we're reading, and then we're going to take this total amount, 4,800 amps, that's an 8 over there, that's going through there, and we are going to go and figure out what that's, how many times bigger this is than that. Okay, so 4,800 divided by 3 gets me to a value of 1,600. In other words, the current that is going through the top over here is 1,600 times greater than the current that is going through my actual CT. Well, what's my CT standard rating? The CT standard rating is going to be 2.5. So I'm going to take that 1,600, I'm going to multiply by 5, and that's going to go and tell me what I'm going to go and have. 1,600 times 5 gets me out to a value of 8,000. So my current ratio is going to be 8,000 to 5 that I'm going to go and have off of here. What's my line current on the primary system? Line current on the primary system, we don't need to use the CT to do any of that. We just have to go and take a look at what we have for current inside here, 4,800. And because it is a delta type of system, we know that these currents are going to be adding together to form something greater. Let's go and do that. We know that our current was given in the question as being 4,800 times root 3, which gets me out to a value of 8,313 amps that we are going to go and have. It's a little bit higher than what is shown inside of you guys' book over here. Inside of your book there, it's showing 4,800 over 5 over 3, etc. Off of these ones here, and the current ratios, etc. The primary line current that they're showing you over here, they also do, well, they just do this thing backwards. If you take a look at that one there, since the CT ratio is 8,000 to 5, they went and multiplied the phase current of 450 that they have in here. I don't even know where they got that value from. Times root 3, which got them to 779.4. So just disregard what's inside of there. Know that your line current is going to be this 8313. We'll stick that in red here, 8313 amps. Beautiful. Okay. One more big set to go through, and this is going to be for my total energy and power metering that I'm going to go and have, where I've got everything connected. Now, we know that when it comes to our metering over here, we can get away with one less watt meter element than what we have for the load. So if I take a look, I've got VT and CT that are together going to go and feed onto a watt meter, which is then going to go and multiply my volts times my amps over here, and therefore it's going to go and give me my watts. Now this is a watt meter. It's not a VA meter or a bar meter or anything like that, which means it's only going to tell me about the true power that is coming out. I'm also going to have to go and take a look at both of these and their ratios to go and figure out my apparent power, my VA, my power factor, all that other stuff. Looking at my currents that I'm going to go and have over here, we're just going to trace over top of stuff once again. Looking at this line over here coming from my watt meter, remember my watt meter is made up of a voltage element and a current element. Actually, that's not going to work. I'll trace it with a different color marker here. We'll just go with the red over here. If I take a look at my watt meter voltage element, which is what this thing is over here, I see that my watt meter voltage element is tracing this path over here, and then through the watt meter actual voltage element over there. So I see it's just measuring that loop over there. Yes, I do have this meter over here that's going to tell me voltage A to B, B to C, C to A, all those other voltages that we can get off the system. But we're not going to bother with those right now. We're just looking at this one over here for its voltage. Same with my ammeter section. We'll do this one in blue for the same line going across from A to B, going across A to B over here. If I trace this out, I'm going to go and see flowing through here, through that ammeter section, coming back through IA alone, and then joining up with the C current to go through the B. We explained this in a previous video. You can go back and take a look at it inside of your lower voltage calculations. But we see that ultimately it's going to go and create just that loop, and this side over here is going to go and measure my amps off of here. Okay, so let's go and do our actual readings off of this thing. They give us a couple of ratings for these. They give us watt meter 1 is 190 watts, so 190 watts. And watt meter number 2 is reading 410 watts that we are going to go and have over here. They show us that PTs have 115 to 1 that they're going to go and have as a ratio. Once again, this is not proper to call it 115 to 1. We want to have this to $1.20, and the CTs are 500 to 5. That is a proper ratio that we are going to go and have. They want to know the total true power, the power factor, apparent power, primary line voltage, primary line current, and my ammeter readings that I'm going to go and have off of here. Well, the first thing that we are going to do is we are going to go and figure out the total true power dissipated by our primary circuit. And we know that we can just add up what we have on our 2 watt meters that we are going to go and have. So 190 plus 410 is going to go and give us our basic value, and then we're going to have to multiply it by a ratio over here. Let's start by doing the 190 plus 410. 190 plus 410, which gets me to a value of 600 over here. So we're going to come back to this one over here. We've got 600 watts multiplied by my overall ratio, 500 over 5 and 115 over 1. So we are going to just multiply those ones together. 500 divided by 5 is the same as if I had a ratio of 100 over 1. And this is 115 over 1. So really, if I take a look at it, it's the same as if I've got 115 over 1 multiplied by 100 over 1. Both of these have got the same denominator over here, which means that we just have to multiply the tops together, which would get us to a watt meter multiplier of 11500, or 11,500 that we would have. So my watt meter is going to be 600 watts, which is adding those two up, multiplied by 11,500. 600, which we already have in here, times 11,500, which gets me up to a value of 6.9 mega that we are going to go and have, or 6.9 megawatts. My total power is going to be 6.9 megawatts. Now I'm going to place that in over here because we're going to start to build a triangle. 6.9 megawatts. Beautiful. Okay, now that we've got the megawatts over there, the next thing that we are going to do is we're going to try and figure out what our circuit power factor is. And thankfully, we have got these two over here that we are going to be able to go and calculate with. We can only do this calculation, though, if it is balanced. Okay, don't try throwing this thing unless they tell you that it's a balanced load. You have to err on the side of the fact that it might not be, and you might not be able to go and utilize this. Because it is a balanced load, we're able to go and do this one where we are going to go and have that inverse tangent, root 3, watt meter, watt 1, watt 2, etc., all that other stuff that we can go and put together into a calculator. Look on your page 42. It shows you that one, we're going to go and put this thing into my calculator. I'll clear that a couple times just to make sure it's completely cleared out. I don't know why it feels better to clear it 3 times, but it just does. Okay, we're going to go and cotangent. That's the inverse tangent. Then we're going to stick in bracket, bracket, bracket of root 3. Actually, I don't think I need all those brackets here. Cotangent of second root 3 bracket. So that's going to automatically multiply by watt meter 1 minus watt meter 2. So that is going to be my larger minus my smaller for 10 minus buck 90 divided by 410 plus buck 90 bracket, bracket, bracket. 3 brackets to go and close this whole thing off. And when we punch that through, we end up with a value of 32.4 degrees. So I know what my phase angle is, 32.4 degrees over here. 32.4 degrees. Now what we can do is we can go and figure out what our power factor is, because power factor is going to be cosine of our angle, cosine theta. So since 32.4 degrees, we're just going to go and take the cosine of that. So I'm just going to go and hit cosine, cosine alpha, answer. Cosine of my last answer, which gets me out to a total power factor of 84.4%. PF, 84.4%. Beautiful. Well, now that we know what our power factor is, we know that our VA is equal to our watts divided by our power factor. So if I've got 6.9 megawatts, I can divide it by 0.844. Let's go into back into here. We are going to go and take 6.9 divided by, and we'll just go and put in our last answer because that was at 0.844, which gets me to a total of 8.173. So we have got a total of 8.173 mega VA. Let's just put that in there. Mega VA that we have over here. Beautiful. Okay, now that we've got our total amount of mega VA, we can then go and take the rest of our voltages and currents and stuff like that. We could figure out anything we want for line voltage, line current, etc. We're not going to go through all of that at this point. I mean, we know what our ammeters are going to be. Well, actually, no, we don't know what our ammeters are going to be reading. We do have to go through it to get out our currents. What is our voltages and our currents that we have off here? Well, they didn't really give us much at this point. It says that our secondary voltmeters all read 120. So we've got at this point 120 that we are reading over here, and that they have got a rating of 115 to 1. In other words, the high side is going to be 115 times that. So let's go and take that 115. So the 120, that's what I'm reading off of my PTs, times 115, which is going to get me to my high side, which tells me that my high side over here is going to be a value of 13.8 kV. Beautiful. 13.8 kV that we are going to go and have off of our high side, which if I take a look at it, I see that I'm going across from A to B, so therefore 13.8 must be my E line. Okay, 13.8. Now that we've got our E line and we have got our total amount of VA, this 8.173 mega VA, we can go and divide out using our VA formula to go and find our total amount of line current. I line is equal to my VA divided by my E line times root 3. 8.173, so 8.173, and I'm just going to start rounding after that. 8,173,000 divided by my value of voltage, 13,800, times root 3, which gets me out to a value of 341.9 amps. So 341.9 amps, that's going to be my I line, 341.9. So we'll call that 342 amps line. If that 342 amps is going through a 500 to 5 CT, that means it's going to come out as 1/100th. Remember, we did this calculation before. We said 500 to 5 is the same as 100 over 1. So we just know that it's going to go and become 1/100th, which means that we're going to be taking 342 divided by 100, which is going to really just move our decimal point over 2 more to the side, which is going to go and bring us out to a value of, so we're going to take 342 divided by 100. 3.42 amps. Beautiful. 3.42 amps, which when you take a look at that and compare that to your book, you're going to go and see that once again, what we have is going to be different. They just divide it by 500 rather than 500 over top of 5, which is what it's supposed to be. But the actual ammeter is supposed to be 3.42 amps. Okay, that covers all of our high voltage CTPT calculations. Very much the same thing as what you saw in your low voltage ones.